Hello, my dear students. Welcome back to my channel. I'm your Sunando, sir. So let's continue with the competency series. We have done 30 questions already in this series, and today we will do another excellent competency based questions. That is question number 31 from the chapter refraction through a lens, and question number 32 in this video itself, that is from machines. You see how beautiful these competency questions are. Let's read the first question, which is from lens chapter. An object placed in front of a lens forms an image of same size. Now here is a very big information given that the size of the image is same as that of the object. Now this is only possible in a convex lens. What happens in a concave lens? In a concave lens, we know that the image formed in a concave lens is always diminished. Means the image in a concave lens will always be smaller than the object size. So when you are obtaining an image of the same size as that of the object, it is definitely with a convex lens. So here one thing is very clear, that this lens is a convex lens. Now, where do we keep the object in a convex lens, or where do we keep an object in front of a convex lens to obtain the image same size as that of the object? So for that you have to look at the ray diagrams. In the ray diagrams, if you see, when the object is kept at 2f1, at that very time, at this position of the object, the image is also formed at 2f2, the other side 2f2 behind the lens, and the size of the image is same as that of the object. This is a very important condition, a very important case of image formation for convex lens. When the object is at 2f1, the image is at 2f2, and the size of the image is same as that of the object. So here again, the picture is very clear that if I try to visualize it through a ray diagram, suppose this is the principal axis, this is the convex lens. Okay. Now, you don't need to necessarily draw the diagram in your answer, but to explain, I'm telling you, this is the optical center, this very point. Here you have the f1, here you have the 2f1, and this is where you're keeping the object, right? Now here on the other side, behind the lens, you have f2 and 2f2. Now at 2f2, you form the image. You see the size of the object and the size of the image would be exactly same. The image would be obviously inverted, real and inverted, of course. Now, this is the scenario. This is how it is placed. The image is of same size as of the object. Now, if I consider this distance, the object distance, let us call this u. In fact, object distance is denoted by the letter u. But we will call it u1 because there is another case also on moving the object 12 centimeter closer to the lens. So for the second case, we will call it u2, the new object distance. So we are calling u1 as the initial object distance. So initial object distance u1 is, what is this distance? From optical center to focus f1, it is f. So from optical center to 2f1, it will be 2f. And since this distance is measured while going to the left side, so it will be minus 2f. Object distance is always negative by sign convention, right? Is it clear? So u1, the initial object distance is 2f. Minus 2f. Why this minus sign? Because of the sign convention. Now, the v1 means the image distance, initial image distance. That is your 2f again, but this is plus 2f because this distance is measured while moving towards the right side from optical center. So if you are moving left side, distance is taken negative. If you are moving right side, this distance is taken positive. We always start the measurement of distances, horizontal distances, from the optical center. Okay. Now, this thing is clear. Now, what is written as the second case? It is written moving the object 12 centimeter closer to the lens. So what we have done, we have brought the object closer to the lens. By how much distance? By 12 centimeter. That means now, let us say the object is here. I'm drawing it with a red color so as to distinguish. So now you see the red color is the new position of the same object. We have brought it closer. By how much distance? By 12 centimeter. Can you see? 12 centimeter I have written. That means the new object distance, new u, let us call this u2. The new object distance u2 is nothing but the old object distance. What was it? The distance was 2f, and you have subtracted 12 centimeters from it. So that will be 2f minus 12. 2f minus 12, isn't it? 2f minus 12. Right now we are talking about the magnitude only, magnitude of this distance, magnitude of this particular distance. So from here to here, the magnitude of the distance was 2f. And we have now brought it 12 centimeter closer. I'm sorry, from here to here, the distance of the magnitude of the distance was 2f, isn't it? From here to here, the magnitude of distance was 2f. And now we have brought it closer by 12 centimeters. So it is 2f minus 12 now, and put a minus sign because the distance is object distance, which is always negative. So are you getting what I have done? This particular distance is the initial object distance, which is minus 2f. The minus sign indicates that it is an object distance, nothing else. If I talk about only the magnitude, that is 2f. And the new object distance is this distance, getting the point, which is 2f minus 12, and put a minus sign before it. So it becomes minus, and then inside the bracket, 2f minus 12. Clear? So let us write all this. What have we done? That u1 is minus 2f, u2 is minus of 2f minus 12. Now, what do we have to find? Now, here another very important thing is told, that when we have brought the object 12 centimeter closer to the lens, the image is 3 times magnified from the object size. Now, in this scenario, the image formed would be, as per the question, the image is 3 times magnified. So magnification is I upon O, right? That means the size of the image becomes 3 times as that of the object size. So if object size is 1, the image size would be 3. 1 multiplied by 3 is 3. So magnification is 3 upon 1, which is simply 3. But don't forget that the image is inverted. So for an inverted image, the magnification is always taken negative. So don't forget a minus sign over here, the minus sign. So magnification comes to be minus 3. Now we know that there is a formula for magnification whose derivation is not in the syllabus. You have to only study that magnification is V upon U. V means the image distance, U is the object distance. So this time we will use this formula here. Instead of M, we will write V upon U. But be careful that this magnification is minus 3. This magnification is for the second case, not for the first case. For the first case, case 1, when the object was at 2f1, the magnification was 1. Because the image of this was of same size, so magnification was 1. And since the image was inverted, so magnification was minus 1. I think I should be writing it in 2 columns so that you do not get confused for 2 different cases. So, I'm writing it like this. Case 1 is when the object is at 2f distance minus 2f distance. U1 is minus 2f. Now, in this case, magnification is minus 1. Why? Because the image size is same as the object size. In case 2 case, this u2, what we are calling is minus of 2f minus 12. Very easy. I hope there's no confusion. Now magnification is minus 3. I just explained you why. Image is 3 times larger than the object. Okay. State the type of lens used. Okay, this is very simple. This answer is obviously we have done long back. This is convex lens. Now, calculate the initial position of the object. Means we have to calculate U1, initial position. U1 is what we have to calculate. Okay, U1 is minus 2f, but we do not know f. First of all, we have to find f. All right. Now, what do? We use the lens formula here. In the second case, lens formula is 1 upon f. F is focal length, which is fixed. F does not change. No matter we are bringing the object closer or farther from the lens, the focal length of the lens remains same. So there is no point of calling f1 and f2. It's f. Even in case 1, it is f. In case 2 also, the focal length remains f only. Now, the lens formula says 1 upon v. So v ke jagah we are writing v2 because we are talking about the second case right now. And u2. So the same lens formula, 1 upon f is equal to 1 upon v minus 1 upon u. Now what we are doing, 1 upon f is equal to, now in place of v2, what we will write, you see. First of all, look at this, m is equal to minus 3. Can we write magnification ka formula is V upon U. And for the second case, we are using V2 upon U2. Isn't it? This is a basic formula for magnification, V upon U, whose derivation is not in the syllabus, but you have to study. So can I write in place of M, if I write V2 upon U2, so that is equal to minus 3 because magnification is minus 3. So V2 upon U2 is minus 3. So we can definitely write what? That V2 is equal to minus 3 into U2, minus 3 U2. Isn't it? V2 is minus 3 multiplied with this U2. Now, in place of this V2, we will use minus 3 U2. So 1 upon minus 3 U2 minus, here we will write as it is 1 upon U2. Now when you solve this, what happens? 1 upon F is equal to minus 4 upon 3 upon U2. So you got U2 is equal to minus 4F upon 3. Very simple. This part, this is a simple calculation. So U2 is minus 4F upon 3. But U2 was this also. So we can equate this value minus of 2F minus 12 with this U2. So both U2s are actually same. So we can write therefore minus 4F upon 3 is equal to minus of 2F minus 12. Don't forget the bracket. Cancel these minus signs. Here itself, it becomes very simple. Now you have a very simple equation with only one variable, F. So when you solve this, you will get F as 18 centimeters. Very simple equation. So focal length has come. Now if this focal length is fixed, it is fixed for a particular length. So this is 18 centimeters. Now we have to calculate the initial position of the object. So that's very simple. Initial position of the object, that is U1, was minus of 2F. Isn't it? See? This is what we have to calculate, minus of 2F. So F is 18 centimeters. So minus 2 into 18, that is minus 36 centimeter. So finally, when you write the answer, you will write initial position of object is equal to 36 centimeter. But of course, do not write the minus sign now. You will write this minus sign in words. What does this minus indicate? It means that the object is placed in front of the lens. So 36 centimeter in front of the lens. So this itself in front of the lens means minus. So this is how you have to leave the answer. And one important answer is left out, that is convex lens. They had also asked, name the type of lens. So you have to write this also properly. The lens is convex lens. So when you leave your answer, in your exam, you must highlight the answers, like, because this convex lens carries marks. The teacher should not find challenging to search your answer. Where have you written answer? It should be clearly visible. And this also you underline it properly, so that when the teacher sees it, the teacher can find the answer very easily. The examiner can find the answer very easily. Then only you can get marks very easily. I hope this first question is clear. Now moving to the next question, next competency based question, question number 32. This is from machines chapter. Where is it? This is not the question. Wait 1 second. I will give you the question. So yes, this is the question. This is the machines chapter ka question. See, this is also very interesting, competency focused. A person lifts a coal piece of mass 250 grams with a pair of fire tongs. So a fire tongs is basically chimta. In Hindi we call chimta, fire tongs. So of length 28 centimeter. So this is 28 centimeter. Now in a tong, where is the fulcrum? This is the fulcrum. And somewhere here you apply the effort, right? So effort lies between load and fulcrum. And here is the load, where you are holding the iron piece with the tong. That is what the question is telling us. Suppose this is the piece of the coal piece, not iron piece, coal piece. Now this mass is 250 grams. So we can convert it to kg, and that is 0.25 kg. So 0.25 kg, but we need load is actually the force, so we will convert this kg to kgf. So we can write kgf, simple. So what have we done? We have done this gram conversion to kg first, so that gives you the mass is 0.25 kg. Now we are expressing the mass in form of weight, because weight is force and load is also force. So it has to be taken in weight. So kg, instead of writing kg, we are writing kgf. We are not converting it to Newton because the value of g is not given. So unnecessarily 9.8 lena hai, 10 lena hai, so that confusion is not there. We are simply we are doing a very clean calculation. We are writing kgf. Okay. Now this becomes the load. So given that the load is 0.25 kgf. Here you have to find the effort. So effort is unknown. But what is told that this length from load to fulcrum is 28 centimeter. This is given in the question. The length of the tong is given. The length of the tong itself is the distance from load to fulcrum, because the load is at this extreme end and the fulcrum is at the another extreme end. So load arm is given. Load arm is given 28 centimeter. Load से fulcrum तक का distance को ही load arm बोलते हैं. Very simple. And effort से fulcrum तक का distance को effort arm बोलते हैं. So we need to find the effort arm. Is it given? See, he applies effort at a distance 7 centimeters from the fulcrum. So fulcrum से effort तक का distance is 7 centimeters. That means effort arm is also given. Very good. Effort arm is also given. Very good. Now we have to find the effort. Now see, here you can go, you can do a mistake. What mistake? Generally, children are habituated to use this formula. Load multiplied with load arm is equal to effort multiplied with effort arm. This formula is very commonly used by students. But this is valid only for an ideal lever. This lever is not ideal. Efficiency is 90%, not 100%. So you cannot use this formula to find the mechanical advantage. You will get a wrong answer. So what we will do, since the efficiency is 90%, we have to be very careful. We cannot use this formula. Now, from this formula, we can see what happens here. Load up, this formula itself can be written as load upon effort is equal to effort arm upon load arm. The same formula. We cannot use this formula to find mechanical advantage, because this is only to be used when the lever is ideal. But in our question, the lever is not ideal, so we can't use this. So, load upon effort is known as mechanical advantage. So you can't write that load upon effort is mechanical advantage and mechanical advantage is effort arm by load arm. No, can't do that. Load arm, can't do this. What happens if machine is ideal? Listen carefully. I'm explaining you a concept now. I'm not solving the question right now. If machine is ideal means if efficiency of this lever is 100%, then of course we could have written load upon effort is equal to effort into effort arm, and MA is equal to effort arm upon load arm. Then this is absolutely okay if the efficiency was 100%. And you know that in a 100% efficient machine, the velocity ratio and mechanical advantage are also equal. If the machine is 100% efficient, then MA is equal to velocity ratio. This is also true always for a 100% efficient machine, because the formula, the fundamental formula is MA is equal to VR multiplied with efficiency. This formula is in your syllabus. And if efficiency is 100% or numeric value is 1, then that means MA is equal to VR multiplied with 1. So MA is equal to VR. So if we consider that our machine is 100% efficient, then instead of MA, we can also write VR, because MA would be equal to VR. And VR is equal to effort arm upon load arm. So ये भी एक formula है. लेकिन we also know that MA depends on efficiency of the machine. But VR does not depend on the efficiency of the machine. VR depends on the design of the machine. So even if our machine is not equal to 100%, VR would be still effort arm upon load arm. That means this formula remains same even if the machine is 100% efficient, even if the machine is 90% efficient, even if the machine is 60% efficient, even if the machine is 40% efficient, because velocity ratio does not change with efficiencies. Velocity ratio depends on the design of the machine. It depends on the effort arm and the load arm length design. So effort arm and load arm is fixed. Effort arm is 7 centimeters, load arm is 28 centimeters. So the design is fixed. So velocity ratio will not change with the change in efficiency. Even if friction increases in the machine, the velocity ratio would remain same. Or friction decreases, velocity ratio would be same. So this formula can be used even when the machine is ideal or even when the machine is not ideal. When I say machine, I'm talking about a lever. When the lever is ideal or whether the lever is not ideal, we can definitely say velocity ratio is equal to effort arm by load arm. But this formula can be used only if the efficiency of the lever is 100%, but not less than that. Now, since our machine is less than 100% efficient, so we will not write MA is equal to effort arm by load arm. We will use velocity ratio is equal to effort arm and load arm, which is the fundamental formula for velocity ratio. And even if our machine is 90% efficient, we can still use the formula. Effort arm is 7 centimeters, load arm is 28 centimeters. So this gives you 0.25. A velocity ratio has come. Now we will calculate mechanical advantage. Velocity ratio has come. We have to find what? We have to find effort, MA and VR. Three things. So one of them has come. Now, mechanical advantage is velocity ratio multiplied with efficiency. This is a fundamental formula. So mechanical advantage is velocity ratio is 0.25. Efficiency is 90% given in the question, 0.90. 90% can be written as 0.90, and which gives you 0.225. Are you getting the point? 0.225, right? 1 second. 0.225. Yeah. So we have got mechanical advantage also. We have got velocity ratio also. So two things we have got. Now we have to find effort. Bahut easy hai. Mechanical advantage is equal to load upon effort. This is again a formula which can be used here, anywhere. This is fundamental formula for mechanical advantage. This is the definition of mechanical advantage itself, the ratio of load upon effort. See, we are not using effort arm upon load arm as mechanical advantage, but we can definitely use mechanical advantage as load upon effort. This formula is the fundamental formula of mechanical advantage. Can be used for any machine, whether 100% efficient or not. Now load is it given? Yeah, 0.25 kgf. So we will solve it in the next line better, because mechanical advantage is already calculated and load is 0.25 kgf. So effort nikalna hai. When you solve this simple equation, so you will get 0.25 upon 0.225 kgf. Now this will be approximately 1.11 kgf. This is your effort. So we have calculated all the three things. Now simply leave the answer in the same sequence as asked. Effort, then MA, then VR. So you can simply write, therefore effort is 1.11 kgf. MA is how much? 0.225. Did I write a unit? No. VR is 0.25. 0.25. Now MA and VR do not have units. Be very careful. We will not write any unit for MA and VR. So now make a box for better visibility, and this is your answer. I hope you have liked both of the two competency questions that we discussed today, question number 30 and 31 and 32 today, and we will continue again with question number 33. Keep tuned to the channel. God bless you. Take care.